Alright, this time let's talk about two pretty classic reactions, oxymercuration and hydroboration. So the reason we care about these reactions is because up till now you've seen some alkene reactions. Hopefully you remember hydrogenation and particularly hydration. So hydration was the method we used of transforming alkenes to alcohols. The unfortunate part was that goes through a carbocation intermediate. So our goal is to find a way to transform alkenes to alcohols that does not go through a carbocation intermediate. And the reason is because anything that forms a carbocation intermediate has the potential to undergo a rearrangement, either a hydride shift, a methyl shift, or a ring expansion. We want selective reactions that don't do that. Okay, so let's look at what chemists have come up with. So this is the reaction we'll be looking at today. Again, you have an alkene, and at the end you have an alcohol. And you'll notice that there's two different places that we could add on the double bond, the less substituted and the more substituted, and this places an alcohol on the more substituted location. Now there's a whole bunch of reagents that are used in the middle here. We're going to talk about those now. So let's look at the mechanism for this reaction. Well, first of all, let's talk about a few things first. So the first reagent you see here is HgO-Ac2. That is mercuric acetate. It actually looks like this. So if you know what the acetate group looks like, it pretty much looks like this. So on either side, this would be one of the OAC groups, and this would be the other OAC group. The other thing you need to know about mercury is it's pretty late in the periodic table. Its electron configuration is 6s2. That means that it has a lot of D-level electrons that it could use. So the particular lone pair that we're going to be concerned about, this one right over here, that a lot of people seem to omit, these are D-level electrons, which doesn't matter so much, but just know that mercury has the potential to have many different lone pairs on it. We only care about representing this one right here. So the other thing we need to worry about is this is the first time you've seen something that's not, well, in a friendly place on the periodic table. So you've seen a lot of non-metals in the top right, you've seen some metals in the top left. This is pretty far down. So the idea when we're talking about metals generally is to pretty much pretend they're a big partial positive charge. So if you see mercury or tin or sodium or potassium, any of those guys, you're pretty much just going to say, all right, this is practically a big positive charge. So for this molecule, the positive charge will be the mercury, and we also should note that the oxygen that's to the left and right of this mercury are capable of accepting electrons. The reason we care about that is perhaps there's some part of the mechanism where this bond breaks. Where are those electrons going to go? Well, they could possibly go on the oxygen. The last thing we care about is, well, I guess I sort of said this out of order, but the lone pair on the mercury comes from those 5d orbitals. Okay, what else should we go over? Well, let's just dive right in, I guess. So now we have this sort of huge, scary looking complex over here, and we have our alkene. So even though this looks huge, you should treat it exactly the same way you treated everything else. So if we had this reaction over here, you would be perfectly okay with drawing the arrows required to do this transformation. Why? Well, you know that simply you're going to treat the alkene as a nucleophile. You're going to attack the H here, break the bond here, and you're going to continue on just like that. The other thing that we've looked at before was this sort of bromine-bromine bond, where once again, you're just going to treat the alkene as a nucleophile, you're going to attack this, and you're going to go through the bond breakage. The only thing that changes, though, is that you have an arrow coming back to the double bond. So I'll tell you that the mechanism for this addition will follow one of these two. remember why this happened and why we formed the bridge to begin with. It had a little bit to do with the electronics that were going on here. So remember, when we're doing this, in this case, we looked at the electronegativity difference between these two guys. So over here, we knew that bromine was electronegative, and the hydrogen was electropositive. So this has the partial negative charge, this is the partial positive charge. The nucleophile is going to attack the partial positive. In the case of the bromine-bromine, we said that as this complex gets closer to your double bond, there is polarization that occurs. And polarization makes the front bromine, the one that's approaching the double bond first, positively charged, and that's where the attack happens. And over here, this is negatively charged, so that's where the lone pair ends up after the bond breakage. So over here, I told you to treat the metal ions, the mercury, as a big positive charge, and so the guy that's right next to it is going to be the oxygen, and we're going to call that our partial negative. So the first thing that's going to happen is the same thing that has happened in the past few lectures. It's just that we're going to get an attack from the double bond onto the electrophile, and that's going to look something like this. Now here we need to think about whether it's going to be just this or is it going to be this, and I sort of already pictured it here. Remember, the reason why you form the bridge is because whatever you're attacking has lone pairs on it. So as the positive charge is forming over here, it has the ability to attack the other one with its lone pair. Okay? So because mercury has this lone pair, it's able to attack back. On this hydrogen, it's being abstracted by the double bond, and it doesn't have a lone pair to attack back and reattach to the bridge. So over here, mercury does have that, so that's why we're going to form the bridge. Okay, and when we form the bridge, it's going to look like this. So as usual, the bond breaks over here, so this group's just going to be hovering over here for a little bit, and the bridge is formed arbitrarily. We chose wedge, so this is a wedge-wedge bridge, and you have the other OAC group still attached. Okay, let's look at what else is being done in the reaction. So I'll tell you that THF is just our solvent, so it won't really play a huge important role in this. The other thing we have is water. Sometimes people do this reaction in base. That works as well. So if you remember the halohydrin reaction, what happened after the initial bridge formed by the Br? We had a Br anion over here, and we also had the water present in the reaction. And we said the water was in excess, and it was a better nucleophile than the bromine. So what's going to happen? Well, the same thing that happened in the case with the bromohydrin. Actually, I'm going to simplify this and say that, all right, here's our water, and let's not worry about these huge molecules, these acetate groups. Let's just call them, abbreviate them as OAC, and not worry about them from here on out. Okay, so at this point, you should know what happens next. As usual, the nucleophile attacks at the more substituted carbon. Again, the reason for that is, if you look at the transition state, this is going to be better able to stabilize the positive charge. And remember, as we're looking at this, we're always making electronic arguments. Here, the nucleophile attacks the partial positive. Here, the nucleophile attacks the partial positive. Here, the nucleophile, once again, attacks that partial positive. Over here, we have this secondary carbon slightly being able to stabilize the positive charge. And so you see our nucleophile is going to attack the partial positive. As you form a bond here, that's again too many bonds to carbon, so a bond needs to break, and that's going to transfer the electrons onto the mercury. And you're going to get something that looks like this. As usual, we have the anti-attack, or the trans geometry, as a result of this water needing to attack under the bridge because it's easier. And now we have this. So this should be rather familiar to you. You should have gotten a lot of experience with this doing the hydration reactions for alkenes. Well, what's going to happen is the water is going to do the same deprotonation as usual. and we are going to arrive at this. So we've added the alcohol that we're interested in, and now we still have this mercury on here. This is where you don't really need to know the ins and outs of what's happening. So a lot of organic chemistry courses will just tell you, all right, don't worry about this step, you don't need to know the mechanism, and I'm going to follow suit with that. So we add this last reagent, known as sodium borohydride. And this is a reducing agent, which I'll explain briefly. So we get this as our final product, and remember, of course, we could have formed that mercurium ion bridge on the other side with the dash dash, and that's why we're going to get the enantiomer as well. So let's talk about a little bit about what's happening during this workup that we're not looking at the mechanism for. So it goes a little bit into boron chemistry, but that's why these reactions are a little bizarre. That's why I wanted you to see the other alkene and alkyne reactions before doing this. So sodium borohydride looks like this. Just like we were talking about with the NaNH2, it has this whole sodium cap thing where once it's in solution, it's going to separate into a positively charged sodium and a negatively charged boron. So I told you, whenever you're seeing metals, just think about those as positive charges. But what's going on here? So remember what group boron is in. Boron is, well, left of carbon on the periodic table. So if you remember that group, that's the group that corresponds to 3. So if you're doing a formal charge calculation, it's going to be the number of, well, the group number minus the number of sigma bonds to it, minus half the number of lone pairs as well. So if we do that calculation, what we get is a negative formal charge on the boron here. So what this means is, well, this is negatively charged, and the significance is this boron prefers to have 3 bonds. It actually wants this bond to break. So what it's going to do is it's pretty much going to, in a mechanism, attach this or throw this hydrogen onto something else. And that's what's doing the reduction. If you actually find the mechanism for this online, you'll see that this bond breaks and is attached somewhere over here, and then some rather complicated mechanistic steps that you don't need to worry about happen, and finally you just get the H added here. Okay, that said, let's look at our second reaction for the day. So again, just to reiterate, this one we just did here is called Oxymercuration. Know the name of that because it shows up pretty prevalently in the literature. The next one we're going to look at is Hydroboration. Okay. And that is going to do something similar in function, but the reagents are different. So again, we have our alkene here. We have a bunch of reagents in the middle that we don't well understand yet, and our product is going to be, again, an alcohol. Now notice our oxymercuration added the alcohol to this location, but our hydroboration is adding it on the right-hand side of the double bond. So again, we have that choice between the more substituted side and the less substituted side, and the hydroboration, I'll tell you, is going to choose the less substituted side. Okay, so let's look at what's happening. This is a strange sort of reaction where we can't actually draw the arrow pushing as our borane, that's what this BH3 group is called, it comes closer to our double bond. What happens is you get a very strange, what is called square planar transition state. And this bracket means that this is a transition state that's different from an intermediate. Generally, if you have an intermediate, that means in some situations in your organic synthesis or in your organic wet lab, you can isolate that actual molecule. In general, a transition state pretty much is hypothetical. It's very hard to actually prove that a transition state exists because this doesn't usually exist in its free form. It's not isolatable. You can't really get a bottle of it, so to speak, after running a reaction because it is already transformed into the product, which in this case will be this. So let's talk a little bit more about what's happening in this square planar intermediate. So it's sort of like the BR-BR where it approaches the double bond, and then we need to think about what's going on here. So I'm going to pull these partial positive and partial negative charges, and we're going to look at this. So the first things first is that on our alkene, you need to think again about this more substituted versus less substituted. If we're looking in the transition state, as we were saying before, because of hyperconjugation, the more substituted side is going to be better able to stabilize charge. So in our transition state, we expect this carbon to be the partial positive. Okay, what about the borane molecule? Well, if you actually look up in your electronegativity tables, you'll find out that this has the very strange property where the hydrogen is actually more electronegative than the boron. So what happens is that the hydrogen, for the first time in a long time, is going to have the partial negative charge, and the boron is going to have the partial positive charge. Now you can understand why this transition state is forming this way. You're again lining up the partial positive and the partial negative. And over here, this is again negative and positive lining up, and this is, well, just like this. So a lot of people will mistakenly draw it the other way around, where the boron or the B will be over here and the H will be over here. That'll get you the B here and the H here, which isn't the correct product, or intermediate rather. So again, always think about the electronics that are happening. So as we're looking at the electrophilic addition, always think about, all right, I have the nucleophile. What's the partial positive? What's the partial negative? Over here, why can this attack back? Because it has the lone pair on your, I guess, intermediate over here on the actual carbon chain. It's always the more substituted that's going to have the partial positive charge. So over here, if you understand how we arrived at these partial positive charges through the electronegativities, then you're going to be able to correctly predict what happens in a lot of these mechanisms from here on out. Okay, so now we're at this species here. Once again, in a lot of intro organic chemistry classes, you're told not to worry about the so-called workup. So here, we're not going to look at the inner workings of the mechanism here. Just know that upon workup with NaOH and peroxide, this group will be transformed into an OH group, and you'll get your final product like this. Remember, the reason why I'm drawing the wedges here is to tell you that it's going to be a syn addition. That's going to be important when you start doing reactions and you have potential for stereochemistry, chirality, all that fun stuff. And over here, we don't need to actually include those afterwards because there's already another H here and there's already another H here. So neither of these carbons are chiral. We could just draw it line wedge without worrying about the wedges or the dashes. Okay, so again, this is hydroboration. So let's summarize what we've looked at so far. If you have an alkene, then there's two different ways you can react it. If you want to add an alcohol to the more substituted carbon, you are going to use the oxymercuration, and this is so-called Markovnikov, because this group has added to the more substituted carbon. And over here, the hydroboration is called anti-Markovnikov, because the OH has added to the less substituted carbon. The way most people think about it is in terms of which side did the hydrogen add to. So in Markovnikov addition, up here, the hydrogen always adds to the less substituted side, and in anti-Markovnikov, it adds to the more substituted side. But if you think back to it, these descriptors aren't very useful because they both obey that same principle of electronegativity differences between the reagents and where the partial positive and negative charges are going to be. Okay, so at this point, I'm going to do the oxymercuration and hydroboration of alkynes. If your lecture hasn't covered alkynes yet, you should stop here. But if you have, let's go on and look at those two. Okay, so the next reaction we want to look at is the transformation of a terminal alkyne to a ketone. And I got careless here, and oh wait, no, that's actually fine. Yeah, to a ketone. So this is 3 carbons. we add the carbonyl here. Okay, so I'll tell you that the mechanism is a little more complicated. So for simplicity, we're going to pretend that this HgSO4 actually just looks like this. So we're going to pretend it's Hg2 plus and SO4 2 minus. You should remember that SO4 is a -2 anion from either general chemistry, or if you remember sulfuric acid is H2SO4. That could dissociate twice and you'll get sulfate as your dianox species. Okay, so say we have this and this. I'm going to tell you that your initial step is going to be exactly the same as it was for the alkene. So it is going to look like this. So again, we have our nucleophile being the alkyne, the triple bond this time, and our electrophile being the mercury ion. The only reason we're not drawing an arrow to break a bond here is because we assume that these were already broken up, which is again just like an assumption we made for simplicity. A lot of different lectures will actually have this step being differently, so just make sure you're consistent whatever your lecture wants you to know. Okay, and again, the reason why we're going to get a bridge when we form it is because Mercury has a lone pair located in its 5d orbitals. So we get the formation of this bridgehead intermediate. Okay, and it's going to be identical to as before. You still have the water there, so water is going to be your next nucleophile. For now, I'm going to drop this sulfate, but remember, charge needs to be conserved, so your sulfate is still here, making the overall charge of this reaction net neutral. Okay, and as the water adds, it'll break the bond here, because remember, carbon can only have 4 bonds. One of these needs to break, and you'll get this. At this point, once again, just like last time, just to show the parallels, you have this OH2 positive charge here, so you're going to do the same deprotonation that we usually do, and eventually you'll get to this step. Okay, so this sort of molecule is actually very special. It has another vocabulary name. So anything that appears like this, a double bond with an alcohol coming off the double bond, is what we refer to as an enol. So if you hear the word enol, it means you have a double bond with an alcohol coming directly off of it. That vocabulary word is pretty important because you'll see a lot of enols, especially when you take organic chemistry too. So the interesting property about enols is that an enol is actually in equilibrium with a ketone by a process called tautomerism. So we will look more closely at that later. So tautomerism is super important, especially in any reactions involving carbonyl compounds, but at this point I think we'd be getting ahead of ourselves if we took a close look at it. So one of the frustrating parts about organic chemistry is a lot of parts of it won't make sense until you've seen everything. Up until then, you're going to have to take a lot of things for granted, and this tautomerism process is one of those. But tautomerism can happen either in acid or in base, and if you remember our original reactants here, we're doing this in H2SO4. So we already involved the HgSO4 in the initial attack. The water was used for the second attack on the bridge, and the acid is used for the tautomerism. Okay? So the other thing you need to know is that if we're looking and comparing the enol to the ketone is much, much, much more stable in general. There are circumstances where the enol is actually preferred, but in general, the extent of reaction, the equilibrium constant, is going to be almost entirely in this direction. So the enol will convert to the ketone given the acidic or basic environment it's in. So that makes our final step of this reaction look like this. The tautomerization process, the enol becomes the ketone, which is starting to look like the product we care about. And finally, what happens is that. And here, I think I might have accidentally took a carbon away. 1, 2, 3. Yeah, so I need to fix that. Over here. Oh, it looks like I actually had this on the entire time. Okay, so I should be a lot more careful. That's an H. That's an H. That pretty much continues through all the way. So if we look at our final product over here, wait, let me make sure. We should actually just for now make that non-H, just say consistent with everything else. Okay, then this is still going to need another carbon. All right, my bad. Assuming everything else is correct, because it looks correct, what occurs is this. Unfortunately, what we're not going to be able to demonstrate is the selectivity that this is going to be Markovnikov, but you'll have to take my word for it. Okay, so over here the tautomerization occurs. We convert from the enol to the ketone, and then we do yet another workup to get rid of this over here. This workup is, again, a little too complicated for beginners in organic chemistry, so we're not going to look too closely at that. Okay, so again, what I was trying to demonstrate is that you get a ketone that is essentially Markovnikov. Let me see if I could still look for an easy fix on that. Okay, yeah, so what I can do is put the H over here, because remember, our water needs to attack the more substituted carbon because that's more stable. So if I carry this through, we should be okay. So at the end here, suppose this was an H, suppose this was an H, and lastly, suppose this was an H. So again, if our double bond was originally here, it had the choice between adding at this location and this location. In this oxymercuration, it's going to add on to the more substituted carbon across the double bond. Okay, let's look at the last reaction for today, and that is the hydroboration of an alkyne. So again, suppose we start with an alkyne and we're exposing it to a slightly different boron reagent that has this Sia that you don't know about yet, and the same reactants in the bottom. Okay, so what's going on with the Sia? The Sia is known as a siamyl group. You could think of it as a big bulky alkane molecule that's attached to either side of the boron. Basically, it makes it so that nothing else can approach while it is forming the transition state with the alkyne. Okay, so in general, it's going to look pretty much the same as last time. This complex will approach the double bond. We'll again get the same sort of transition state, and over here the H will be adding to this side because it's more substituted. It has that partial positive charge, and the H in this case has a partial negative, and this will add here. So as a result, we get this. And at this point in time, there's actually not much more to do. Suppose that you do the same workup as last time, and you could either say, okay, I get the alcohol and it's oxidized by peroxide, which is an oxidizing agent, to the aldehyde, or you could say, okay, I get an alcohol here, and then I do the keto-enol tautomerization once again that we saw in the previous reaction, and we get this as your final product. So maybe it was a little unclear, but I'll show you the main idea for these two. So the summary. Say I start off with this, either an alkene or an alkyne. In either case, you could react them through the hydroboration pathway or the oxymercuration pathway. If we're looking at the hydroboration pathway for the alkene, what we're going to get is the alcohol adding to the less substituted carbon in the double bond. And if you look at it for the alkyne, what you're going to get is the carbonyl compound that is on the less substituted carbon. So this is technically an aldehyde, but to keep it in simplicity's sake and to draw a parallel between this, I have omitted that last hydrogen that comes off here. Okay, and for the oxymercuration of the alkene, what we get is the alcohol on the more substituted carbon in the double bond, and for the alkyne, we're going to get the carbonyl on the more substituted side of the triple bond. Okay, and we talked about this before. With the hydroboration, we're calling it anti-Markovnikov because of the fact that this went on the less substituted and the H adds the more substituted. And if you remember that intermediate, it was a square planar intermediate. In contrast to the oxymercuration, where again we were doing a Markovnikov addition, which means this adds the more substituted side, and we once again formed that bridge that we saw in a lot of the halogenation reactions. Lastly, you need to memorize these reagents in case you ever need to use them on an exam. So you'll see that they're actually pretty similar. If you compare the hydroboration reagents over here, once again, this will probably be done in THF, you'll see that the only thing that happened was we modified the borane to dicyamal borane, which is, again, these bulky alkane groups are attached just to protect the transition state of the alkyne when you're doing that. Over here, this is a little different. So again, oh, did I forget? No, we didn't need this, did we? Maybe I forgot it. No, we don't need a reducing agent. Okay, yeah, because we don't need a reducing agent here because of the tautomerization. So remember what each of these guys does. This forms the bridge, this is the solvent, this performs the attack on the bridge, and this does the reduction. Over here, we have this that forms the bridge, this that does the attack, and this that does the tautomerization. Okay, hopefully that made some sense.